50 meters below the surface, off the coast of the Faroe Islands, a machine the size of a small aircraft is flying underwater. With a 12-meter wingspan, the 28-ton mammoth sweeps through a figure-of-8 loop 70 meters wide, tethered by just a single cable in complete darkness. This is the Dragon 12, a tidal kite designed to feed 1.2 megawatts of power into a national grid. And in March 2026, after a 10-month test, it was finally hauled back to the shores of Vestmannaeyjum and replaced by a smaller 100 kilowatt Dragon 4. This is the first step of a microgrid project by Minesto, the company behind the Dragon tidal kites, part funded by the Swedish Energy Agency and run with Faroe's utility SEV. And they have plans to build 200 megawatts of tidal kites across 7 Faroe sites, with ambitions of powering a high proportion of the archipelago's energy needs. So, what is a tidal kite? Who else is building these? And could this innovative design really be the answer to generating power from the ocean? Minesto was founded in 2007 as a spin-off from the Swedish aerospace manufacturer Saab. Its product line, called Deep Green, has more in common with an aircraft than a power station. There are 4 core parts: a wing, which generates lift, a nacelle slung beneath it carrying a turbine directly coupled to a generator, control surfaces, rudders, and elevators at the rear, exactly like a plane's tail, and a tether, one cable that anchors the machine to the seabed and carries power and data back to shore. Dragon 12 is the utility scale model. 12 meters across, 28 tons, 1.2 megawatts, and a 10 times scale up of the 100 kilowatt Dragon 4. The whole design sits behind 92 patents in 12 patent families. Here's the first question every engineer asks: why not just bolt a turbine to the seabed and let the tide spin it? There are 2 reasons for this. First, water is dense, roughly 800 to 1000 times denser than air. So current moving at walking pace carries enormous energy, but it moves slowly. Most tidal streams run between 1 and 3 meters per second, and a fixed turbine only ever sees that speed. The second reason: power scales with the cube of speed. Double the speed through the turbines and you get 8 times the power. So Minesto doesn't leave the turbine standing still, it flies it. Instead of making the water go faster, Minesto makes the turbine go faster. Think of a kite on the beach. Sweep it sideways across the wind and it races along far faster than the wind itself. Same principle, different fluid. Steering in a figure 8, the kite drags its turbine through the water several times faster than the current it's moving. And thanks to the cubic relationship, several times the speed becomes many times the power. Flying a 28-ton object on a string underwater is the hard part. The kite is autonomous. An onboard control system continuously works out where it is and moves the rudder and elevators to hold a pre-programmed trajectory. For Dragon 12, a figure of 8 is roughly 70 meters wide, at an average flight depth of about 50 meters. It's supervised from the shore through a SCADA system and a human-machine interface, but nobody is driving it with a joystick. Electricity from the generator travels up a cable inside the tether, onto a seabed umbilical, then ashore. The tether meets the foundation through a latch that unlocks, so the kite can be surfaced, towed into harbour, serviced and reconnected. Even the anchor is engineered. For Dragon 12, instead of a heavy gravity base, the team drilled and grouted a tubular foundation. This provides a smaller footprint, quicker and quieter to install, and creates less carbon. And the flight path itself is a turning dial. In May 2025, Minesto added 10 extra meters of tether to Dragon 12. That let it fly a bigger loop and sweep more water and lifted power performance by around 25%. 10 meters of cable, a quarter more electricity. Minesto isn't alone in tidal energy, but its approach is unusual. The mainstream is rotors. Scotland's Maygen project in the Pentland Firth is the world's largest tidal stream array. 4 seabed mounted turbines totaling 6 megawatts. And Orbital Marine Power's O2, a 74 meter floating platform with 2 1 megawatt rotors on retractable legs, is the most powerful tidal stream device in the world by rated capacity. Running at the European Marine Energy Centre in Orkney since 2021, it has reported capacity factors above 40% and availability above 90%. The closest thing to a rival kite is Dutch. Sea Current's Tidal Kite doesn't spin a turbine at all. Its wings oscillate back and forth. That motion drives a hydraulic converter. The company closed a €4.8 million funding round and is deploying at Ameland in the Netherlands and Pampelbourg in France. Minesto meanwhile has spread beyond the Faroes. An 80-megawatt site under development at Holyhead Deep in North Wales, partnerships in Taiwan, and in January 2026, selection by the European Investment Bank for advisory support on a 10-megawatt Dragon farm in EU waters. So how much energy does it actually make? Honestly, today, not much. Dragon 12 is rated at 1.2 megawatts, Dragon 4 at 100 kilowatts, and the whole Vestmannsund site tops out around 1.4 megawatts. For scale, a single modern offshore wind turbine is around 15 megawatts, so one turbine equates to about 10 times the site. However, the plan is where the numbers turn serious. Hesfjord, the fjord feeding the capital Tórshavn, is the first true array. Minesto's design work puts the first phase at roughly 10 megawatts, scaling up to 30 megawatts from 24 Dragon kites, with an estimated annual yield of 84 gigawatt hours. That one fjord alone would be equivalent to about 20% of the total Faroes electricity consumption in 2021. Then the full roadmap is of 200 megawatts across 7 sites. Vestmannsund, Hesfjord, Leviksfjord, Skopunafjord, Svínoyarfjord, and 2 more still unconfirmed, supplying roughly 40% of the island's electricity. This represents an important step for the Faroe Isles. In 2024, the island generated around 480 gigawatt hours, and 43% of that still came from heavy fuel oil and diesel. Wind supplied 32%, and hydro supplied 23%. The target is 100% renewable electricity by 2030. The strongest argument for tidal, however, is predictability. Wind and solar have to be forecast. Tides, however, are astronomy. You can print a table of the currents in Vestmannsund for the year 2050 and it will be right. Minesto's specific bet is that flying lets you work in slow water. The company says its plants generate in flows as low as 1.2 meters per second, and that a Minesto plant weighs up to 15 times less per megawatt than competing technologies. Steel per megawatt is the biggest lever on whether marine energy gets cheap. If both hold at array scale, the map of usable sites gets far bigger than the handful of violent tidal races this industry has been fighting over for 20 years. Published estimates put tidal levelized cost of energy at roughly 11 to 45 US cents per kilowatt hour. That's 2 to 4 times what onshore wind costs. The UK has raised the dedicated strike price for tidal in its subsidiary actions by 29% just to make projects bankable. And innovation power contracts for small marine projects have started around £290 per megawatt hour. Tidal does not survive without policy support today. And on scale, Maygen at 6 megawatts is still the largest tidal stream array on Earth. Then there's durability. Dragon 12 came back to shore showing wear and tear after exceeding its own service intervals. That's useful engineering data. It's also a reminder that seawater, biofouling and fatigue loading remains undefeated, and that the whole design rests on one tether doing 3 jobs at once, holding 28 tons, carrying the power and carrying the data. And finance. Minesto is a small listed company burning cash, with hundreds of millions of Swedish krona in capitalized development costs, and an October 2025 rights issue in which only around 41% of the shares were taken up through subscription rights. The timeline is now tied to the balance sheet, and Hesfjord, the array that would prove all of this, is in mid-2026, still a design and a site assessment. A kite that flies underwater. This is an elegant answer to a hard physics problem. The ocean holds enormous energy, but moves too slowly to spin a turbine hard, so instead of waiting for the water to move faster, you move the machine.